So this is Chapter 4, Section 3. We've already covered Newton's first law. Now Newton's first law is also known as the law of inertia. Okay? So today we're going to cover the second and third law. His second law says the acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the object's mass. So if we put some symbols to this, it says that acceleration, that's A, is directly proportional to the net force. So you could rewrite that like that. That means the same thing. Or acceleration is inversely proportional to the object's mass. So if I want to say proportional to, I would say 1 over mass. That is the same thing as saying acceleration is inversely proportional to mass. We're going to get to that. They give us a formula that goes with this too. Your net force is mass times acceleration. So force equals mass times acceleration. They don't give us this, but I know this was also a homework question that talked about the units for, I think it was the units for force. But if you look at the units for mass, what's the unit for mass we commonly use? Okay, kilograms. So force is Newton. And what's the units for acceleration? Meters per second squared. So in our previous homework when it said, okay, what's the SI unit for force? And you said Newton, and it said this is derived from what other units? And the answer was kilogram times meter over second squared. That's how they get this, because force is mass times acceleration. Now we're going to go look at a video.
Imagine a hockey puck sitting on an air hockey table. The downward force of the puck's weight is exactly canceled by the force of the air jets pushing up. If there is no net force on the puck, Newton's first law is enough to understand the motion. But what if there is an unbalanced force? Imagine a hockey puck with a sail. The force of the wind from the fan can slow down the puck, stop it, and make it accelerate in the other direction. We can learn about the amount of force that was used if we measure the mass of the puck and its acceleration. Newton's second law shows the exact relationship between the net force on an object measured in newtons, its mass measured in kilograms, and its acceleration measured in meters per second squared.
So that summarizes Newton's second law. Again, you've got a formula that goes with that. Force equals mass times acceleration. And his second law talks about how our mass and force and acceleration are related. What's directly proportional, what's inversely proportional. For Newton's third law, it says if you have two objects that interact, the magnitude of the first exerted on object 1 by the object 2 is equal to the magnitude of the force simultaneously exerted on object 2 by object 1. And these two forces are opposite in direction. So that is the one that you've learned. It says for every action there is an equal and opposite reaction. And because these two forces coexist, either force can be called the action or the reaction. And on our next slide, we're going to get into action and reaction pairs. How can you have a scenario and consider what is the action, what's the reaction, and it can always be swapped up. For every action, there's an equal and opposite reaction. So, action-reaction pairs do not imply that your net force is going to be 0 on either one. The forces are equal and opposite, but either object may still have a net force on it. So that means once one is applied a force to the other, there can still be a net force left over at the end, and it can be for either one. The example they're giving here, and I know you're going to have some more examples within within your homework, but it says, consider that you're driving a nail into wood with a hammer. So you got your nail, you got your hammer, you got the wood. You got 3 different things that you're looking at. The force that the nail exerts on the hammer is equal and opposite to the force that the hammer exerts on the nail. You could say that just the opposite way too. But there is a net force acting on the nail which drives the nail into the wood. Is there also a net force that's going to be acting on the hammer? Typically what happens when you hit the nail with the hammer, what happens with the hammer? It immediately bounces back, right?
Yes.
Typically that is a pretty typical reaction there too. So you can list this either way. You've got the force of the hammer on the nail. They're calling it the force of the wood on the nail, but you can also say hammer on nail and then nail on hammer. Either way. What about another action-reaction pair? What if you had, say, a semi-truck and a small car that collide head-on? Give me the action-reaction pair there.
The force that the semi-truck exerts on the small car is the same as the force that the car exerts on the semi-truck.
Yep. Will there be a net force left over?
Yes.
Yes.
The semi-truck will pile over this small car.
It could be. But, you know, there's definitely other reactions that happen afterwards. It's not just one-on-one. There's typically a chain reaction if you talk about something like that. And you can have multiple action-reaction pairs after that. So let's look and see what this video wants to tell.
Asserts that forces always act in pairs. For example, a car accelerates by causing its wheels to turn and push against the road. It is the force of the road pushing back against the car that makes the car go. Note that the forces are simultaneous. The car puts a force on the road at the same time that the road puts a force back on the car. The forces act in pairs and have the same magnitude, but it is a mistake to think that the forces together would cancel each other out. The force on the car makes the car accelerate. And the force on the road, which is firmly attached to the earth, makes the earth accelerate, although only by a very small amount. Adding the force on the road and the force on the car does not make sense because the forces are applied to different objects with different observed results. A force on the earth doesn't affect the car, and a force on the car doesn't affect the earth. Newton's third law holds for non-contact forces as well. Consider the effect of the earth's gravity on a paper airplane. When the earth pulls downwards on the airplane with a force of 5 newtons, the airplane pulls upwards on the earth by the same amount.
So make sure they spent most of the time on this one talking about contact forces. So your contact forces, that was like the car on the road, giving you an action-reaction pair there. But it also holds true for your non-contact forces. What's that?
It's going to crash.
I don't think so. I don't think you're.
Theoretically rotate the earth.
I don't think so. I don't think it's going to work that way.
We will move the earth in the opposite direction a little bit if everybody on the earth traveled one way.
I don't think that you're going to be able to detect it.
Be able to measure it.
Yeah.
Yeah, but